Hi, I'm Ben-Yaakov. This presentation is entitled Dissecting TI's Active EMI Filter. There is a relevant video to this presentation. Here's the link, and I'm going to print the link on the page of the YouTube video that you are now watching. There is also a disclaimer here. The commercial device mentioned in this presentation is shown for educational purposes only. No endorsement or recommendation is implied. In the controller LM25149, it's a DC-DC controller, Texas Instruments implemented a circuitry for active filtering of the ripple, or EMI, that is to suppress or attenuate the ripple that goes from the unit, from the converter to the input. It has some internal circuitry and then some external network that you need for this to operate. In this presentation, I'm going to present an overview of active power filter in general, just a short introduction. I'm going to do an analysis, a simulation of parallel active power filter, which is the family of filter belonging to the subject we are discussing. I'm going to cover the TI design of the active EMI filter, and then to point to some of the flaws in TI's analysis and explanation, and finally to wrap up with some conclusions. So what is the problem we are addressing here? Here I'm showing a DC to DC converter, a buck synchronous converter, and we know that when this upper transistor is on, the current of the inductor is actually injected or drawn, you might say, from the bus. Consequently, if we look here at the bus, we see here pulses of current, could be high current. In the application we are going to discuss, it's going to be like 8 to 9 amp and high frequency. And obviously there is a lot of ripple here. There is a DC, but there is a lot of ripple. We are putting a capacitor to capture this AC component, the ripple component here, but there's no escape from the fact that some of the ripple will go on and penetrate into the source. This is not allowed by a number of standards, such as the CISPAR 25, because it is interfering with other units in the system. So how is this ripple actually tested to see whether the design complies with the standard? We're using the so-called LISTEN, which is Line Impedance Stabilization Network. Basically, it's composed of an inductor, a large impedance here, and then a bypass, capacitor, and resistor. And the idea is to capture the ripple here on this branch. I'm showing it for like a grounded system without earth. In general, you'll have here actually 3 lines. So I'm saying it for, say, battery operated system. And in this case, the current will be passing through this 50 ohm, and if we'll measure the voltage across the 50 ohm, it is actually representing the ripple that is injected from the system into the source. Now this impedance should be high so that the current will be passing through here rather than going back this way, so this impedance at the frequency of interest should be high. Now just take an example. If the requirement is 40 dB microvolt, and usually it is stated in dB microvolt, which is 20 log the voltage here divided by 10 to the 6, that is, it is referred to 1 microvolt, then the voltage is 10 to dB microvolt over 20 to the power of times 10 to the minus 6, and the current is this voltage divided by 50 ohm. So 40, it's going to be 100 microvolt divided by 50, so it's 2 microamp. So it's fairly low signals we are talking about. The requirements are fairly strict. So how do we solve the problem of attenuating these signals, the ripple, the noise? And this could be by a passive network, like showing here, the capacitor. It's a pi network. And the idea is, of course, to lock the current here and then have a high attenuation here. You might have another impedance here. So this is a passive approach. There is an active approach in which you use an amplifier or another active device in order to emulate a circuit that supposedly has an advantage in that, say, it's smaller, more economical, rather than having a passive component, which might require the fairly large size inductor and high capacitance capacitors. So this is the idea of active filter. Now, there have been a number of papers, quite a bit as a matter of fact, publications of proposing different ways. I'm showing two of them, old ones, just the first generation, you might say. Here we have from 1995 a paper by Hamil and Poe. And what they are actually showing is that if you have a source which is injecting ripple, you can measure the current here and then sync it by a dependent current source such that the remnant, the rest of it, will be small. So the idea here is to reduce the current here by feedback. So this is one way, by using a current source. Another way is the circuit that is shown here, and this is a paper written by Professor Kolar and co-workers in 2006. And this is like a parallel connection. I'm going to call this a parallel active filter. And here what is really being done is to emulate a low impedance. So this circuit is actually emulating a low impedance by active circuit, that is by an amplifier. So we have an impedance here, so this is a sort of a T filter. We have high attenuation here because this is a low impedance, and then there is a high impedance blocking the current from going into the source. So this is the parallel active filter, and here they are showing the performance. This is without the filter, this is with the filter, and this is the boundary of the standard that they are trying to comply with. So how do we emulate a low impedance? Well, the idea is, of course, to use the Miller effect. And Miller effect, we mean by that an amplifier in which we have an impedance between the output and the negative input. And we can show that this results in an impedance which is lower than this one. And this is because the voltage here is A times V in, minus. So the voltage across Z sub F is V in on one hand, minus A V in on the other hand. So across it, it's V in times 1 plus A. And therefore the current will be V in times 1 plus A over ZF. And if we sort of calculate the impedance that we see is the voltage times the current, and it comes to be Z sub F over 1 plus A. And this is, of course, very well known. If you have a capacitor here, then you get a Miller capacitor, which is this capacitance times 1 plus A, so the impedance goes down by 1 plus A. So this is a way to get a low impedance using elements with higher impedance, which are supposedly less expensive and smaller. Now the amplifier can be built around an operation amplifier with two impedances, Z sub 2 and Z sub 1. The gain is, of course, Z sub 2 over Z sub 1 minus, because it's an inverting amplifier, and therefore the impedance seen at the input of the whole network here is Z sub F, this is this one, divided by 1 plus A. So this is very well known, and this is a way to emulate a low impedance. So now, if we have this low impedance, and we have two impedances here, we connect it here, then obviously we're going to have a attenuation here, high attenuation, and then this is blocking again the current. So this would be the structure of a parallel filter. Another way to draw it is just to move things around, and I'm doing it because it is now like what is published and in the datasheet of Texas Instruments, in fact. And what I'm showing here is this is the circuit I used to explain the operation, and here it is by moving Z sub F here, and Z sub 1 here, and then putting this in between. This will be now another way of sort of drawing it. It's the same circuit, of course. And here it is, see it here, we see the two impedances and the amplifier and the impedance in between. This is basically this circuit. So again, the objective here is to emulate a low impedance such that we'll have a high attenuation in this filter. So this is what Texas Instruments has implemented in this LM25149. We have here this network, here it is, two impedances and the third one, and then obviously we're going to have an amplifier here. It doesn't show, and I haven't found too much information about this amplifier. And again, we have this connection here. So this is really a parallel filter, as I've shown earlier. Now, there are a number of problems with this circuit in general, and I'm going to go over some of them, at least two. One is oscillation, passive oscillation. If you inject a current here to this bus, and if these impedances are of low damping, that if you have just capacitors, inductor, another capacitor, this circuit will oscillate because of passive oscillation. It's a network, high Q, high quality factor. So in order to suppress these oscillations due to these injections, and I'm showing it here, you have a circuit, and it's a resonant circuit. You inject pulses here, it's going to have oscillation. So you need to lower the Q, that is the quality factor. And traditionally, this is done by either adding resistors here, or a resistor in parallel to the inductor, or all of them, or a combination of these. So this is what Texas Instruments is showing here. Here we have one resistor, another one. They're not saying anything about these, but these probably have ESR also, so they are to some extent also damped, but again we have it here and here. Now another issue is the self-resonant frequency of these capacitors. Now this switching regulator, which is a buck, synchronous buck, operates at 2.1 megahertz. Now obviously the self-resonant frequency of this capacitor has to be much higher than that, otherwise it will not act as a capacitor at all. So this is something to watch when you are selecting these components for this design. So we have an issue of oscillation, we have an issue of self-resonant frequency, and also we have an issue with dynamic instability or possibility of instability. This is a rather complex circuit here, a feedback circuit. There is I'm showing it here, there's feedback here, there's a feedback here. These are now for grounded, this is low impedance. And therefore, there is some phase shifts, phase lags as a matter of fact, which of course will reduce the phase margin. And so this circuit can actually get into instability, dynamic instability. So it has to be stabilized by proper compensation here, changing some of the parameter. So this is some of the problems that you have to worry about when trying to use this circuit. Now in the explanation, Texas Instruments shows that this circuit is like measuring the current and then generating a current source that will absorb the current. Well, this is not correct, of course. This is the circuit indeed, and we are not measuring the current, we are measuring the voltage. And we are generating a voltage here such that this impedance will be low impedance and therefore will have high attenuation. So this is the way it actually works. There is another issue here, and Texas Instruments is explaining that you have a divider here, so this inductor, this impedance, and then this impedance reflected here, and this is the attenuation, but they forgot about the source. Well, it really depends on the impedance of the source. If the impedance of the source is low, then obviously this is incorrect and you'll get another attenuation factor, and in fact you'll have a current going into the source if the impedance is low. This actually represents the source. Now, as it turns out, in the whole discussion, application or data sheets, etc., Texas Instruments neglect this thing. So Texas Instruments treat this as if this is an open circuit. Again, if this is an open circuit, then of course this stands by itself, but in reality, of course, if, for example, you have a low impedance source connected to this bus, then this doesn't work, because the operation of this depends on a ripple here, and if you have a low impedance, all the current actually will go into the source, and this will not be operated. So treating it as an open circuit without talking about the impedance here is really not a way to go. Now, in reality, we're going to have at least some stray inductance to the source. So we have to take into account what is this stray inductance. And also, if you do the measurement of the ripple or the remnant voltage across the 50 ohm by the listen, you are bound to have some wired cable which has an impedance. So you must talk about this. Now, in actual design, in publication that you'll see, always the author put an impedance here, so you can control it, you know what it is, so you can design the filter for it and not just leave it open, question what it is, then the operation of this circuit without referring to what happens here cannot lead to a good design of the filter. So this impedance is very important, and this is what is done, for example, in this paper by Professor Kolar, Ertl, and others. Next thing I'm going to do, I'm going now to analyze the actual circuit that TI is proposing. I'm not going to go into the detail how these values were selected, but this is not the objective here. The objective here is to understand how the selected components operates, okay? So we have here, this is the Z sub F, it's a capacitor and a resistor, which was put in for damping. Then we have this C sense, which is the input to the amplifier. This is the amplifier here, and the feedback here is this circuit, okay? So we have Z1, ZF, and Z2. Z2 over Z1 is the gain here. Now, generally, Texas Instruments is talking about reflecting this capacitor and emulating a lower impedance, like a larger capacitor. So let's have a look what is going on with this D sub F. We have a 0.47 microfarad, 3 ohms. Now obviously at low frequency you see 0.47 microfarad, but as the frequency goes up, then of course there is a breakpoint here at which the impedance at the frequency, the impedance here equals that of 3 ohm, and beyond that it is 3 ohm, because this is like a short with refer to the 3 ohm. And as it happens, this breakpoint is 100 kilohertz. So we are working here at 2.1 megahertz, which means that in our operating region of frequency, this is a resistor. So we are reflecting a resistor and not a capacitor. So this capacitor really doesn't play any role, being large enough. So you can put another value, it'll be the same. I mean, as long as the breakpoint here is below the 2.1 megahertz. So this is a reflection of a resistor. Now let's have a look now at this impedance, okay? This is the Z2, which determines the gain. So this is 50 kilo ohm in parallel to 1 nanofarad plus 200. Again, at low frequency, it's 50 kilo ohm. This is very high impedance. Then we start to see the 1 nanofarad. And then at a given frequency, it actually becomes 200 ohm. So here it is, high frequency 50 kilo ohm, going down, and then 200 ohms. As it turns out, this breakpoint is 800 kilohertz, and we are working at 2.1 megahertz. So again, we are just above this frequency breakpoint, and so it is primarily resistive. Well, there is some remnants, of course, of the capacitance, so the lagging, but it is primarily resistance. Now we come to Z sub 1. This is a capacitor, 0.1 microfarad. At 2.1 megahertz, it is like 0.75 ohms. Okay? Now we understand now that the impedance here is close to 200 ohms. So the gain from here to here is Z2 over Z1, so it is 266. So the gain we have in this amplifier is 266, and therefore the reflection of this impedance, the Miller effect you might say, is then this impedance, which is 3 ohms at 2.1 megahertz, here it is, divided by 1 plus A, well, 266, 267, so it's 10 milliohm. So what we see here is actually 10 milliohm here. So indeed we are getting a low impedance. Now 10 milliohms is probably close to the value of the output impedance of this amplifier in closed loop. So one has to take into account that there is some additional impedance here at the amplifier. It is not purely like a voltage source here. So now we come to the explanation of Texas Instrument, and they are saying that the gain of this unit is dependent on C sense and C AEFC, the active EMI filter. Well, this is not correct. As we have seen, it's primarily this resistor and not this capacitor. And secondly, they are saying that the filtering here is due to the L sub in, that is the impedance of this inductor, and this capacitance which is reflected. This is here, this capacitance which is reflected. This is incorrect again, because here we have a resistor. It's not a capacitor. So there is no capacitance here at 2.1 megahertz. It's a resistor. So I'm afraid that this explanation is just incorrect. In order to test the circuit a little bit better and to understand what's going on, I've set up a LT-SPICE simulation, and I'm showing first of all an AC simulation to see what is the impedance here of this circuit. So the values here are exactly as the network proposed by Texas Instrument. Here I've chosen an amplifier with high bandwidth. Why do we need a high bandwidth? The reason is that if we need a 266 gain at 2.1 megahertz here, and if this is the open loop gain of the operation amplifier, obviously we need an amplifier which has a gain higher than this 266 at 2.1 megahertz. Okay, so it has to be like 300, 400, whatever. This will imply that the unity gain bandwidth product needs to be something like 600 megahertz. So this is a very wideband amplifier that you need if indeed you'd like to suppress ripple of 2.1 megahertz. So I've chosen this amplifier, which is supposedly of high bandwidth, and we'll see that. I found it in the LT-SPICE library. So here it is. Let's first of all look at the operation amplifier itself, the open loop. Once I'm injecting here a signal, I can look at the ratio between the output and input of this amplifier, so I can actually tell what is the open loop gain of this amplifier. So here it is. This is the open loop gain. This is of course the amplitude. This is the phase, which I'm not interested in. And we see that indeed this is high bandwidth, well, 10 megahertz, 200, but then the behavior is kind of strange. I've put here a 0 dB line, so it sort of converges to this, and the gain is just not good enough, okay? So what I did, I just built my own amplifier. That is, using dependent sources. I've put here together an amplifier which has a 10 to the 5th gain at DC or low frequency, has a RC for shaping the bandwidth, and then it has some buffer here and a clamp so the voltage will not go very high or very low. So this is sort of a self-made amplifier. And here is what I'm getting. First of all, let's have a look at the amplifier. This is the RC behavior, and indeed the RC that I've chosen brings here a gain bandwidth product of 1 gigahertz, which is very nice, of course. And so this amplifier certainly serves this purpose. Now have a look at the impedance. So this is the impedance that you see. This is just dividing the voltage by the current that goes into here. And what I see here is kind of a funny behavior around the frequency that I'm interested in. Well, there is a dip here, there is a phase shift here. Well, I don't know what is going on. It might have to do with the circuit, the network around the amplifier, or the amplifier itself. So it seems to me that this is somehow due to a extra phase shift that we might have here, and therefore which kind of reminds us of the problem that we have with this circuit, which is the derivative. This is the circuit that we have. This is the input impedance, and this is the feedback, and we know that in a circuit like that you might have problem of oscillation because there is a phase lag here, and then the phase margin is getting smaller and smaller depending on the amplifier. So it is well known that in order to operate this circuit, this derivative or differentiator circuit, you have to put here a resistor. So this is what I did. I now put here a 2 ohm resistor so as to dampen the circuit a little bit, to compensate a little bit better. And indeed, when I run it now, it looked much better. This is now the amplifier itself. And now the reflected impedance indeed starts very high. Why is that? Because at low frequency, this is very high impedance. So the ratio of this impedance to this one is very low. So the impedances that I'll see is very high. And then it goes down as expected. And at this region of 2 megahertz, it's 30 milliohm. Well, remember that we have found by a very approximate analysis and approximate calculation 10 milliohm, so it's pretty good. It's very close to what we have found, so the impedance is indeed very low. So now, as the saying goes, the proof of the pudding is in the eating. So now I've actually set up the whole schematics to actually test the circuit in the time domain. This is a transient analysis here. In this case, we have here a pulsating current source, which is sort of emulating the buck converter. These are pulses of 8 amp and duty cycle of 0.5. The frequency, the switching frequency is a little bit high, 2.5 megahertz rather than the 2.1. And all the rest of the circuit is exactly as suggested by Texas Instrument. And I've also added the listen here. This is the inductor, this is the bypass capacitor, and this is the 50 ohm. Now this is too low. Unfortunately, I just could not run the simulation with the larger inductor. It got stuck, there was conversion problem, there was oscillation, so I just could not run this circuit, and consequently I settled for the value here that I could run it. So it's not ideal, it's not optimized, but that's what I could do. I just couldn't make it operate with a higher inductor. And here is what I'm getting. So this is the voltage at the output across the 50 ohm. And this is like a triangular waveform, which means that the Q, the quality factor of the circuit, is indeed low. And we find here the peak is about 1 millivolt, which is 60 dB microvolt. That's a little bit higher than the CISPAR 25, a little bit higher than that. I'm also showing the current here in this branch and in this branch. Ideally, you like the current here to be, of course, very low, and this is why I like to put a high impedance here, but unfortunately I cannot do that. So if I look now at the current, they are of the same order of magnitude, which means that this is really not optimal design at all, and that this is an underestimate here, so that because there is another current which is not measured by the 50 ohm, but it's a 1-to-1, so the increase here is like 3 dB, so it's not that much. I've also run a simulation with a lower resistance here. Remember that I've put this 2 ohms in order to dampen the circuit when I was injecting here a voltage source. So perhaps in this configuration I can run it with 1 milliohm, which is like a low impedance here, low ESR for the capacitor. And in this case I'm getting something which is sort of consistent with what we got earlier in the frequency domain, in the AC analysis. We see here now, rather than triangular waveform, we see a sinusoidal waveform, which means it's more reactive. The amplitude is a little bit lower, 40 dB, which is close to the norm, but again, this is not the real circuit because the listen is incorrect. Again, we have here, these are the 2 branches. This is the input ripple, and this is the listen resistor current. So this is just for getting an impression of how this circuit actually works. I have also done an analysis of the loop gain of this amplifier. This is an AC analysis again, and you can do it by introducing a voltage source here and actually taking the ratio between this voltage and this voltage. And this is because if you look at the circuit, this is like an input going in here and going all the way back and then to the output. So this ratio between here and here is in fact the loop gain, the closed loop gain of this amplifier, which is very nice because you can see like the phase margin of the circuit. If you are using the circuit and you are testing it, debugging it, tuning it, I highly recommend that you'll actually do this measurement on the hardware itself. Now this can be done by introducing a resistor here, small resistor, and using a network analyzer. I'm showing here about the 100, and in this case you are injecting an AC signal. This is very similar to the AC source that I've put in, AC signal here, and measure the ratio between the voltage here and the voltage here, and this will give you the loop gain under the operating conditions. So this is a very nice way to go to understand what is going on. So in the simulation, this is what I got. First of all, let's have a look at the crossover point, and this is the loop gain, and here this is a 0 dB again line, and we see the crossover is like 200 megahertz. It's a high bandwidth amplifier that I've put. And the phase margin is pretty good. It's about 90 degrees. So this is pretty good. So the system is stable. But there is a lot of wingling here and phase shifting here due to the fact that you have a lot of RNC circuits which are at given frequency becoming resistive, capacitive. So this explains all this jumbo mumbo here. And in order to sort of see it a little bit from a different angle, I'm presenting it here in the Nyquist domain. You can get the Nyquist graph by actually pointing here and right-clicking and selecting Nyquist. So here is the Nyquist. Now the crucial point is here, the -1, 0. You can't see it because the scale is just too high. It's a high gain here. So I'm zooming here, and here is what you see, where there is a lot of encircling here, but you are not encircling this point. I'm going to zoom later on to see it closer. So from the point of view of stability, there is no problem, okay? And in fact here I'm zooming in, and this is now the 0 point, so this is -1, 0, and for the circuit to be stable you have to avoid encircling this point, and we are not. In fact, we are penetrating this unity circle at 90 degrees, which is consistent with the phase margin of 90, which we have seen in the Bode plot. So everything is consistent here, but the operation is kind of questionable because of these reactive and oscillatory behavior. So let me wrap up with some observations here. First of all, active EMI filtering is workable. I mean, you can operate it. It works. It's not something that you cannot operate, you cannot design, but it is very complex and prone to oscillation and instability, so it's not going to be a very simple task to design something which is stable, reliable under all operating conditions, and the spread of the values of the component. And then we understand that the source impedance plays a major role in the performance. So you have to design it for a given input impedance of coming from the source. Without that, you'll design it and then you'll put it in the circuit and it might not work properly. And then comparison to a passive filter was not done in this work. I didn't do it, although Texas Instruments is presenting some comparison. I think this should be done independently in order to see how much do you really gain with this active filter. And the point is that the active filter is actually making you a large capacitance capacitor, okay, emulating it. Now, you can put a large capacitor, large capacitance capacitor, and the question is, what's the penalty? Is it too big? And can you compromise? Can you maybe change the filter a little bit? So this is something to be looked at, and this was not done in this work. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you found it of interest and perhaps it will be useful to you in the future. Thank you very much.